Okay, I wanted to start today by talking about vectors and do some more about linear combinations and the transpose, as we briefly mentioned at the end of last class, but I wanted to kind of expand more about that. So first of all, let's define what a vector is. So I know there's a physics definition of vector, and this is the definition we're going to give now is not even the full definition, which we'll talk much more about later. But specifically, when you think about vectors in space called Rn, this is what they are. And it's very simple. It's just n by 1 or 1 by n matrices. Yeah, so this will be 1.4. What we're doing right now is still in 1. At the end of 1.3, but we've actually done already some 1.4 stuff. So it's kind of muddled. So that's it. It's n by 1 or 1 by n matrices. So can someone tell me like what that looks like? So what does n by 1 mean? Can someone give that in terms of rows and columns? Like how do these look different? Like how many rows and columns does n by 1 have? Yes, n rows and 1 column. So that looks like a big column, right? And what does 1 by n look like? So yeah, a row. So in particular, n by 1 columns are usually called column vectors. And 1 by n are usually called row vectors. These are, I will use the word interchangeably between, when I say vector, it may just make sense, if I mean column or row. For example, if I do like ax equals b, kind of what we're talking about last time, do you have an idea of what, in most cases, do you think x will be a row or a column? Think about, dimensions and how matrix multiplication works. Do you think this thing will be a row or a column most of the time? Yeah, probably a column, because if this is n by 1, right, then a could be a lot of things, right? It could be m by n, right? But if it was the other way around, if x was a row, 1 by n, then what's the only matrix you can multiply to a 1 by n matrix or vector? What would the dimension need to be of a to be able to multiply n by 1? Yeah, it would need to be a column. So the only way you can multiply a row vector is by a column vector, because of the dimensions. So we'll talk a lot more about vectors later, but just to kind of give a name to things we've been talking about. So for example, like the columns and rows of a matrix, you can identify them as the column vectors of the matrix. So again, vectors will have a lot more meaning later. Just kind of take this definition kind of with a grain of salt now, because it may just seem arbitrary, but it will have more meaning later. So now that we have a name for vector, we can talk about linear combinations of vectors. Okay, so let's kind of review what linear combination means. So here's just a very, very easy question. Find the linear combination of the vectors 1, 0, and 0, 1 that give you 2, 3. So what does linear combination mean? Can someone remind me what that means? If you remember. So apart from matrices, yeah, so it has its own definition aside. You can use matrices to say something about linear combination, but main thing is with scalars, right? All linear combination of these two vectors is some scalar times the first vector plus some scalar times the second vector. So this encompasses all linear combinations. So give me an alpha, give me a beta, then that is some linear combination. Encompasses all linear combinations. That's what a linear combination is. Okay, I think you can figure out what alpha and beta are, right? Just look at it. What do you think alpha and beta would be? There's only one choice you can make. Yeah, it's a very easy one. Alpha equals 2, beta equals 3 is the linear combination. That makes 2, 3. So it's not always going to be the case where it's so obvious that you can just kind of guess what alpha and beta are. So then we have some tools of how to figure them out in those cases. So let's just do another one. Combo of 1, 2, and 2, 3 that give -1, 0. Okay, so you set it up just the same way. I want to find a linear combination. That means I need to find specifically what it is. And the main thing I don't know at this point is what are the scalars? So these are the things that I want to find. Okay, so now how do we do this? Well, let's just say what this is. What happens when you do the scalar multiplication of the two vectors? What is alpha times 1, 2? So now we're doing algebra to find alpha and beta. So what is alpha times 1, 2? Yes, 1 alpha and 2 alpha. So alpha, 2 alpha. And then similarly for beta times 2, 3. 2 beta and 3 beta. So these two statements are the same, and these both give you -1, 0. Okay, so now how do you add these two vectors? Remember, we add vectors or matrices coordinate-wise. So you take the coordinates and add them together. So if I add these two together, I get did I make a mistake? Alpha plus 2 beta, 2 alpha plus 3 beta. Sorry, wouldn't it be 2p alpha? The 2 alpha is coming down from here. All right, so now we know that these are two vectors, the same dimension, and we say they're equal. So they're equal only if, the x coordinates are equal and the y coordinates are equal. So what does that do? That forms a linear system, right? You have two things going on. You have alpha plus 2 beta is equal to -1, and you have 2 alpha plus 3 beta is equal to 0. These two things must be true. we're going to see how you form a linear system from there. So really right now, this is just an application of matrix algebra. So I can form a linear system. They don't even have to be lines on the plane. They're just two linear equations that must be true simultaneously. Okay, so at this point, can someone tell me the augmented matrix that's formed by this linear system that can help us solve it? What does that look like? 1, 2, -1, and 2, 3, 0. Okay, so now let's solve it. So we know how to do this, so I won't ask every single step. So row 2 minus 2, row 1. So this is a -1, this is 2. And then we can do negative row 2. While we're at it, let's just do reduced row echelon form and do row 1 to row 1 minus 2, row 2. So -1 minus 2 times -2 is plus 4, so this makes 3. Okay, so what's the solution? What's my alpha and beta? This is my alpha column and this is my beta column. Yes. So alpha is equal to 3 and beta is equal to -2. So what does this mean? So we just on algebra to find out that 3 times our original thing in front of alpha, 1, 2, minus 2 times whatever we had for beta, 2, 3, is equal to -1, 0. Now let's check it. Is that true? Yeah, I mean, what we're doing here is the explanation of why you can skip to the matrix, right? I mean, once you've seen, this, then you may know in your head how to skip to the matrix, but this is a precise reasoning of how you can even just form the matrix. So let's just check it. So this makes 3, 6 minus 4, 6, which good is equal to -1, 0. So good, we did it. We found the linear combination that gives you -1, 0. Okay, any questions on that? Let's do another one. So same question, but of 0, 1 and 0, 2, that make 1, 1. Okay, can someone give me the obvious answer? So I'm gonna write it out and then you tell me what's weird about what I'm writing. Yeah, no answer. Can you give like an intuitive reason why? Yeah, no matter what alpha and beta you pick, right? When you multiply, you'll get always 0 alpha plus 0, 2 beta, right? So any linear combination will always give you a 0 as the first coordinate. So certainly just you can't do it. But for the sake of just practice, let's just see what happens in the algebra that makes this bad. So yes, it's very obvious that can't do it, but let's just see what happens in a linear system. So I think you can see right now, it says that 0 equals 1 and alpha plus 2 beta is equal to 1. So, you know, you could even do the augmented matrix. And this is a no-no. That means no solution. Yep, so you can't do it. And again, you don't have to go through the process of that. You can just, you know, say quite clearly why this is impossible. Okay, so let's do one more. Same question. 3, 2, and 12, 8 that make 1, negative 1. Okay, so with any linear combination problem, your first thing to write is alpha times the first plus beta times the second. If there was a third, you might say gamma plus whatever the third is, right? Doesn't have to be 2, but if there was, that's what you would write. And this is equal to 1, negative 1. So I want to find out what alpha and beta are. Okay, so let's go through the process that we did for the other ones. This is 3 alpha, 2 alpha, plus 12 beta, 8 beta. And yes, you could see that there is a quick way to get to the matrix, but this is the reason why you can even form a matrix. So the only way for these two vectors to be equal is that the coordinates must be the same. So the first coordinate, 3 alpha plus 12 beta, would need to equal 1, and the second coordinate, 2 alpha plus 8 beta, wouldn't need to equal the second coordinate. Okay, so can someone say the augmented matrix? Yep, 3, 12, 1, and 2, 8, negative 1. Okay, all right, so let's do some row operations. What do you think is a good step to do? How do you do it when you don't have a 1? Do you know what yeah, can you do like, what would be your, how would you do it in one step? What would you be your row 2? There is something dividing by 3, yeah. And then what goes up there in the numerator? Well, if it's 1, then you don't zero out this, right? Negative 2 does that. So the dividing by 3 makes it 1, and the negative 2 eliminates this entry. But it's not too bad because 12 is divisible, you know, by 3. All right, so this gives you 0, and then what's 2/3 of 12? Can someone say that? 8. Oh, how convenient, 0. And then what's this? Negative 1 minus 2/3 times 1. What's that? That is negative 5/3. Yeah, the important thing, it's not 0. And why? What's the conclusion here? No solution. There is no linear combination that gives, I believe it was 1 negative. Now, you tell me, can you just look at 3, 2 and 12, 8? And can you can you make up a reason why you could maybe have figured this out from the beginning? What's the relationship between 3, 12 and 12, 8? Yeah, 3 times 4 is equal to 12, and 2 times 4 is equal to 8. So essentially, though, you can think of they're kind of like the same vector. They're just scaled a bit. And so in one sense, you can think of, right, when you wrote out this line here, alpha 3, 2 plus beta 12, 8. Well, like you just said, 12, 8 is just what? 4 times the vector, 3, 2. Right? So essentially, this is just like a linear combination of one vector. So, and then you can see there, you can't multiply anything by 3, 2 to get 1, 1. I mean, well, if I pull out a 4 from this vector, I get 3, 2 back, right? So I'm pulling out a 4 here.
I was thinking is like, because the first row or alpha is 2, and then beta is alpha times 4, which is 8.
Well,
so can't you write alpha 3, 2 plus 4 alpha 3, 2? I mean, 4 alpha 12, 8.
you could probably work around the numbers a bit. But do you see how this is true from here? Like how I can like factor out a 4 here and get 3, 2?
Yeah.
So do you see how like you get 4 beta from there?
Oh, I
Just
see.
by
Okay.
factor. There's another constant, probably 1/4. You could factor out from 3/2 to get 12 eighths. But the main idea is that like, because here's kind of the big idea is that 12, 8 is already a linear combination. And this is of 3, 2. So we'll explore later of like, why this gives something that doesn't work. But that's, for right now, it's the idea is that if one vector is a multiple of the other, then it's hard, there's less likely to be a solution. Sometimes there is, but not for -1, for example. Okay, so I think hopefully we're okay with linear combinations now. So in the homework, you have specifically linear combinations of columns in a matrix, but all you're doing is this here, forming a linear combination and solving for the coefficients. Okay, so just want to review again what transpose means. And we're going to prove a neat property of it. So we did this last time, but I just want to spend more time on it. Could someone remind me what transpose means? So that's the transpose of A. Yes, the idea is that rows become columns, rows and columns flip. So based on that kind of intuitive idea about rows and columns flipping, what do you think? So for given any coordinate ij in the matrix, what is his corresponding coordinate in the transpose? Like, what would the subscripts be? Good, yeah. So since the rows and columns flip, doing the transpose of a matrix flips, the coordinate. So the ijth entry in the transpose is exactly the jith entry in the original matrix. So, for example, if I do 1, 2, 3, 4, 5, 6, transpose. So this entry is the 1, 2 entry, right? So this will become the 2, 1 entry in the transpose. So that one's over here. 2, 1 entry. Where does this entry go? The 1, 1 entry? Still 1, 1 because I and j are the same. So we keep doing this. So 3, this is the entry 2, 1. So where does this entry go to in the transpose? Yes, 1, 2. So this entry is 1, 2. So this entry down here is 3, 1. So this goes to 1, 3. This entry here is 2, 2. So that goes to 2, 2. And this last entry here is entry 3, 2. So it goes to 2, 3. Okay, so so that's the transpose. So let's do a neat proof about what the transpose of a product of matrices is. So first of all, let's just remind ourselves the definition of the product. So the product of a matrix, I won't ask you to type it out because it's long, but what is the ijth entry of the product? Well, it's equal to the sum from k equals 1 to k equals n, where what is n again? In the product a times b. Yeah, it is the end of the sum, but what specifically is n in terms of the matrices A, B? A column and B row. Right, so remember that the only way you can multiply two matrices is if like kind of the inner dimensions, if you write it out that way, are the same. Can someone remind me what the dimension of the product is? When you do the multiplication, what's the dimension of the product? Yes. It is n times r. So that's this here. So these is the dimension of the product. Okay, a little reminder. And what you're summing over to k equals n is precisely, these equal dimensions. Okay, so when you sum over the elements in A for aij, what remains fixed when you do a product, the row or the column of A? So, the row is fixed and I'm summing over the entries in the column. So that gets the changing index. Now in matrix B, what remains fixed? The other way around. The thing that remains fixed is, but not I, but J, is the column remains fixed and you're changing the row. So just to see, right, you're summing over so you're fixing a row in the first matrix and a column in the second matrix. And these are the terms used to multiply to get an entry in the product. Okay, so let's think about what it means to take the transpose of this product and see if we can come up with some general formula. So let's think about the transpose after producting. So we have AB ij transpose is what in terms of the coordinates of AB? What do you do to the rows and columns in the transpose? Ji. And now let's say what the formula for the jith entry in the product AB is. So now the index is kind of weird, but it's going to be AJK and then BKI. You agree with that? So the A gets the first one fixed and B gets the second one fixed. Oh, the plus, it's supposed to be a T. T for transpose. So I'm saying, what are the entries in the transpose of the product AB? So those entries are precisely the flip-flop of the normal AB. Is that okay? What do you mean B doesn't change? B is, so this is just the jith entry in AB, the product AB. Oh, it's okay. So now the goal is to kind of come up with an expression in terms of transposes where I can maybe make a formula that this is equal to maybe something in terms of the transpose of A and B. So notice, let's try to do it. Let's, if I took the transpose, like what are these in terms of the transpose of their respective matrices? So like if I want to reword this in terms of transpose elements, what is JK, AJK in terms of in the transpose of the matrix? What entry is JK in the transpose? Not KI, but KJ, because that's here. But I get it. And then B would be, oh, I'm sorry. Did I say? I said KJ. And B transpose, you would flip these and get IK. Everyone see that? So I'm identifying those entries JK are just the KJ entry of the transpose. Is that okay? Okay. So you tell me, does that mean that this is equal to A transpose B transpose? Like look at the definition, look at the formula or the expression here. Is this precisely A transpose times B transpose? No, it's not. Yeah. What do you think you could do to make this a formula for the matrix multiplication of something? It's almost the matrix multiplication of something, but yeah, can you may just say what's off about it? Where should the index be? Where should K be for this to be a matrix multiplication formula? right? For the matrix multiplication formula, the K kind of needs to be sandwiched in between, right? Confused? Can you say what you're confused about? Like, at what point does it become confusing?
Could you go over that second summation, the ATKJ?
This one here?
Yeah.
Yeah. So this is just the formula for the transpose of a matrix. So so if I want to look at the IJ, let's just give an actual number. Look at the element 2, 3 in A. When you transpose it, what does it become? 3, 2. Right. The 3, 2 entry in the transpose is equal to the 2, 3 entry in A. That's just the definition of transpose. So if I have the entry A, J, K, what is its entry in the transpose? KJ. So do you see that's what we did here? So AKJ, right now, there's no reason why I'm doing this. I'm trying to relate something in terms of the transpose. So I'm just seeing, let's just see what happens if I look at these as transpose elements, not as A and B elements. Do you see that that switch over to the transpose? Okay, cool. Okay, so yeah, so I think someone said it before. In this expression here, the K's are in the wrong spot, right? The K's are on the ends here. But in the normal definition of matrix multiplication, these K's need to be like on the inside, right? Can you do something to make the K's on the inside? And remember, this is just numbers that you're multiplying. What happens if I put A and put it on the other side? I can do that, right? Those are just pretends like 2 times 3. Now I'm just writing it as 3 times 2. Everyone get that step there? So now is it okay? Is this a valid, this is a matrix multiplication, yeah, right? What is it? It's the B transpose A transpose of IJ. So the AB transpose of IJ is the B transpose and A transpose of IJ. So therefore, these, so all the coordinates are the same. That means what is AB transpose? It's just B transpose A transpose. This weird kind of, so it's like the transpose thing is not distributive, but first you have to flip it and then distribute it. So it's a neat formula. Don't think it's the other way around. Don't think it's A transpose B transpose. It's a nice formula to have. Yeah, so that's exactly right. So we would even do like an example is that if you multiply 0, 1, 2, 3, 4 times 5, 6, 7, 8, and then take the transpose of this, it's the same as doing just the transpose of each. So what would that be? 1, 2, 3, 4 times 5, 6, 7, 8. Oh, but I did it wrong, didn't I? Yeah, it's B transpose and transpose. It's 5, 7, 6, 8, 1, 3, 2, 4. So reason, yeah, so the idea is that in this form here, I could not figure out what, you know, what was this the matrix multiplication of, right? Because it wasn't the K's like, the K needs to be, you can think of like in the middle. So, but if you just flip flop the A and B, then the K becomes in the middle. And then is, right, that was just our definition of the matrix product, is that the rows, the columns of the first matrix are changing and the rows of the second matrix are changing. Could you also, yeah, so this first one is AB, then T, the product. So whatever that is, 5 plus 14, that's just, right, 5 plus 14, 6 plus 16, 15 plus 28, 18 plus 32, then transpose of that. These should be the same numbers, the same matrix. Does that make sense? Like, so, yeah, so taking the product, sorry, this is equal to 5, 6, 7, 8 transpose, and this is equal to 1, 3, 4 transpose. Okay, so just a neat, you know, proof. You know, it's getting us used to the summation formula and of how to work through, you know, this notation. All right, so let's do one definition about symmetric matrices, which we'll come back to later. If the transpose doesn't do anything, then A is called symmetric. So let's see, why do you think it's called symmetric? All right, so if A transpose is equal to A, what do you think? So ATIJ is equal to AIJ for every single IJ. If that's true, well, first of all, what is ATIJ? You know, if you didn't know this was symmetric, this is AJI. So that means that if you flip the columns and rows, that, yeah, the columns and rows, nothing changes in the matrix. So can someone guess why it's called symmetric based on that? Yeah, symmetry over what, you think? Yeah, you can say symmetry over the diagonal. This diagonal line. Yeah, so these two enter the same, these two are the same, these two are the same. So probably won't get to do it today, but maybe next time we're gonna talk about graph theory. And there's a certain matrix that you can form based on a graph that happens to be symmetric. And it's kind of very obvious why it would be symmetric. But for right now, this is just a definition. You might have a homework problem based on the symmetric matrix, but for right now, this is just a very, you know, just a definition. Any questions on that definition? Oh, by the way, if A transpose is equal to A, yeah, here's a little question. If A is symmetric, what's the dimension of A? Good. It must be square. So let's remind ourselves why. So let's say A is n by n. What's the dimension of the transpose? Right, you flip rows and columns, so it's n by m. But now if A is equal to A transpose, that means the dimensions must be the same. So the m by n dimension must equal the n by m dimension. But the only way that can be true is if m equals m. M equals n. So symmetric matrices only make sense in terms of square matrices. So there is actually, in the homework, there's a problem that asks about the validity of A transpose A and A transpose. So, just based on this definition, you could probably maybe figure out, why that's true, just based on what transpose does. So there's that. All right, so any questions on symmetry and transpose right now? It's a pretty simple action. Just flip-flop rows and columns. All right, so this is now technically kind of the beginning of 1.4, which we already talked about some of them, the properties of matrix algebra. Okay, so let's just recall some of the ones that we did before. That, remember, we defined addition, and we proved it was commutative. Right, that was because that Aij plus Bij was equal to Bij plus Aij. We proved that it was associative. I won't do that one, but it was A plus B plus C is equal to A plus B plus C. Can someone remind me what the identity was? What is a matrix that you can add to another matrix such that it doesn't change? Yeah, all zero. The matrix with all zeros. Can someone remind me what the inverse is? So additive inverse means what is the matrix that you add to a matrix such that the result gives you zero? So for example, yes, it's negative A. So -1 times the matrix is the additive inverse. Okay. Okay, so let's, one thing we have is scalar multiplication. This means if you have a number times a matrix, what does that mean? Is that whatever the ijth entry is, all it is alpha times the ijth entry of the original matrix. So essentially what you're doing is multiplying alpha to every entry. So we've done this one a couple times. So now let's get to the big one, matrix multiplication. Okay, so when we first started talking about multiplication, I asked you to kind of think about doing composition of functions in the plane. So let's do the result of that question. Let's do x-axis reflect, then 90-degree rotation. Does anyone remember what x-axis reflect is? What the matrix looks like? Yes, xy to x negative y. So the matrix is 1, 0, 0, negative 1. And do you remember what 90-degree rotation was? This one was, I think, the harder one to see. Yes, negative yx. So this was 0, negative 1, 1, 0. Okay, so now let's do this matrix multiplication. What do you get? What do you get in the first entry? So what do you get in the 1, 1 entry? Zero, yeah, it's all right, 0 times 1, then negative 1 times 0, so that makes 0. Okay, what do you get in the 1, 2 entry? 1. 0 times 0 plus negative 1 times negative 1 is positive 1. All right, what do you get in the 2, 1 entry? You get 1. And what do you get in the last entry? So 1 times 0 plus 0 times negative 1 is 0. Does anyone remember what this reflection is? Almost, it's y equals x. So this is kind of like when you do an inverse of a function, you flip-flop y and x. This is xy to yx. So now let's do the opposite composition. It's 90-degree rotate, then x reflect. Okay, so that's 1, 0, 0, negative 1, 0, negative 1, 1, 0. Okay, so let's do it again. What do we get for the first entry? Right, 1 times 0, 0 times 1 is 0. How about the entry next to it, the 1, 2? Negative 1. How about the 2, 1? Also negative 1. And how about the 2, 2? 0. So here's a great example that matrix multiplication is not commutative. So they're different. Right? If it were commutative, then these would need to be the same. Right? But we've just shown a counterexample that AB is not necessarily equal to BA. Now, does that mean that AB is never equal to BA? No. Can you find a pair of matrices where AB is equal to BA? And when thinking of it, think of the most boring matrix they can think of. Okay, everything is the same number. Yeah, so, or A equals B, yeah. Sometimes AB is equal to BA, right? What are those times? A equals B, right? Obviously that would be true. You said where everything is the same number. So what do you mean by that? So like 1, 1, 1, 1, and like 2, 2, 2, 2. That looks the same. I would say those are the same. Another way of saying that is if maybe B is equal to a scalar times A. Can you think of a very boring matrix? What's the most boring matrix you can think of? All zeros, yeah, that would work, right? 0, 0, 0, 0 times anything. Yeah, what is that? 0, 0, 0 times anything is what you think? Yeah, all you're multiplying is 0. So if either A or B is 0. And there's one other one. I mean, there's plenty more. There's one more obvious one. What's that? Did someone in here? Okay. How about this one? What is the function that doesn't do anything on the plane? So it sends xy to xy. It doesn't do anything. What does that matrix look like? So this is, the 0 function is pretty boring, but I think this is equally boring. Can someone say what that matrix looks like? It's not 1, 1, 1, 1, 1. This would be 1, 1, 1. Sorry, what do you mean? What was the 1? What was the question? What is the matrix that doesn't do anything? So in terms of functions. So this would be the function. F of xy is equal to xy. So nothing. So when you do the function, nothing changes. So the proposal is 1, 1, 1, 1, but that does change it. Yeah. So what is identity? We'll say more about what and why is it identity, but what is that? What is identity? In terms of functions, we can say exactly that's identity. So what does the matrix look like? Forgot. Well, here, how about this one? Yeah. What is the matrix of this function? It's 1, 0, 0, 1. So that will probably be true. A, I, A. So, I mean, this is a special one that we'll talk about what it looks like in higher dimensions. And this will be later the multiplicative identity. We're not there yet, but it's a matrix that does that. All right, I think we have time for one full and very long proof, but it's hefty. And here's another property of matrix multiplication. It's not commutative, but it is associative. So what does this mean is that if you take you have a product of three matrices. You can multiply them in any order you want, grouping. You can't rearrange it, but you can decide which you want to multiply first. So first of all, let's think about dimensions here. Okay, let's say if A is m by n, what must B be? What dimension must B be? N by something. So let's say R. Okay, so now what is the product? Dimension the product. M by R, good. Okay, now if I want to multiply another matrix by the result, what must the dimension of C be? R times something. Let's say, what did I say? Q. So now what is the dimension of the product here? M by Q, yes. Okay, so now if we claim this thing is associative, this multiplication, let's just make sure, the dimensions should be the same if it's associative. So let's just double check that. So we said A was m by n. We said B was n by R. We said C was R by Q. What dimension is B times C? N by Q. And then what dimension is this one? The Q doesn't matter if the N matters. That's why I picked it. Q is just some random number, but the R is the important one. And yeah, so the product of A times BC would be M by Q. All right, so I probably won't have time to finish this proof, but I'll start it. Okay, so let's think about what are the elements of the matrix AB times C. So doing AB first and then times C. So just by a normal definition of matrix multiplication, I'm summing from K equals 1. Now let's look at the dimensions here. What am I summing to? So I'm saying I've done the AB product first, and then now I'm multiplying by C. So which of these letters here should I sum up to? So this is K equals what? Do you remember what letter that should be? So N is if I multiply A and B together, but I said I already did that. So now I'm multiplying A, B, and now I'm multiplying C. R, yeah. So I'm really looking at this step here. Okay, so now it's your normal matrix YR. Because, so this M times R, that's the dimension of AB, right? And R times Q was the dimension of C. And this K index always runs up to this shared, dimension. So that's YR. So by definition, it's AB, and the I stays fixed, the row stays fixed, and then the K changes, and then in C, the K changes, and the J is fixed. All right, is that okay so far? I see a Now it's going to get a little messy. What is this? So right now, this is just normal matrix multiplication, right? So pretend AB is just one letter. It's just IK, KJ. It's going to get a little messy. Okay, now let's forget everything else and let's only look at AB, IK. We have a matrix multiplication definition for that, right? So now we're ignoring everything else. That's a sum in itself. Okay, so I don't want to use K because I'm already using K for something else. So let's use a different letter. I don't want to use N either because that's going to be up here. Want to use Z? Sure, we can use Z. So Z equals 1 to Z equals, what does Z run up to? Yeah, Z runs up to N. Why N? Because I'm looking at AB, and N is this common dimension there. So it's going to be just like normal multiplication, AIZ, BZ, it's not a Z, ZK. Okay, now there's a CKJ over here. Okay, so now this is a little confusing. There's two sums going on. So if any of you have programmed before, this might look familiar, like a nested for loop. So the idea is that first you start in your case, and what do? Well, you do the first step. So what are you summing up? Well, you're summing up this sum. So let's look at this sum now. Right, you're adding up all these entries from Z to N, and then you finish, and then you repeat the algorithm and add 1 to K, and then you repeat it starting from Z equals 1 to Z equals N. So there's two summations going on. Does that make sense? So it's a little hard to wrap, maybe a bit hard to wrap your head around, but there's two sums going on. Now let's think about something in the sum. Is that, look at this term out here, this C term. The C term does not have a Z in it, right? And this sum out here has no Z. So just by process of just the commutativity and associativity of just summation, what we can do is flip-flop the two sums. So instead of the first sum outside being K's and the second being the Z's, why don't I make the first one be the Z's and the second one be the K's? Do this with normal normal addition. And what's left is A, I, Z, B, Z, K, and then C, K, J. So I'm doing a couple things here. First of all, I'm like distributing the C term inside the sum. Think of it as a constant. There's no Z in here. I can like distribute.
Figure out the quick scope timing. I can do it on a film too.
I think someone has their mic on. right? This is this whole distributive property going on. And then I have this associativity where I can rearrange the order in which I do this. So now we've constructed a double sum that now I can group things a bit differently. So let's think about this term here, AIZ. Notice that in this summation, what's after the A? This should be an I. So notice in this summation, when I run from K equals 1 to R, does this term change? Does the AIZ change when I run from K equals 1 to R? No. So what is that like when you normally do addition? What can you do if every term in the sum has the same factor? It's a constant, so you can pull it out. So let's do that. And we're done. Why are we done? What does this equal? This is a matrix multiplication for something, right? What is this? B times C. Let's make sure so just look at the dimensions, right? The K's are okay, and then let's make sure that R makes sense. B times C, right? R is the thing you want to sum. That's the correct dimension. So what is this entry? It's the BC. What's the index of the entry? What's down here? ZJ, yes. ZJ. And now I have Z equals 1 to Z equals N, AIZ. And what's this now? This is A times BC. And then what is the index, right? The Z's are the same. And what's the index down here? IG. So what did we start out with? We started out with AB times C IJ. This was our start. So that was associativity. So maybe a little hard to see the double sum going on. But essentially what we're doing is just a bunch of just distribution and kind of associativity and commutativity of sums. Okay, so we'll prove that matrix multiplication is distributive next time. It's this is the hardest one of the proofs. And then we'll discuss what the identity matrix is. So that'll be next, so Monday. All right, so I'm gonna stop recording.